Well, good evening, ladies and gentlemen. Our question tonight is, are we alone in the universe? So, welcome to this program, The Search for Life in the Universe of the 2010 World Science Festival. And tonight, we're going to talk about one of the most exciting questions for humankind. A question of great interest to all of us. It has inspired scientists, philosophers, even filmmakers, as we've just seen. What we do not yet know is life a one-off chance, a chance occurrence that only occurred on this planet, planet Earth? Or is it, as my Rockefeller University colleague Christian de Duve thinks, a cosmic imperative? That is, the universe is teeming with life. We have just yet to find it. This evening, we will talk about how life might have begun on this planet and how we might find extraterrestrial life in our solar system or even beyond our solar system. We will probably also ponder about how the discovery of ET might change our view of ourselves. There are many ways to tackle these problems, and tonight we are privileged to have an impressive array of panelists who are using different strategies in this search. So I'm going to ask my panelists to join me this evening. Could you come on the stage, please? So I'm first going to introduce our four panelists. Starting on the left, Jill Tarter, astronomer, a founding staff member of the SETI Institute, who directs the Center for SETI Research. This year, the Institute, in case you don't know whose acronym stands for Search for Extraterrestrial Intelligence, is celebrating, quite amazingly, its 50th year of using telescopes to search for radio signals from the Earth's galactic neighbors that could indicate beings elsewhere in the cosmos. She's also a member of the Kepler Space Telescope Science Working Group. So that's Jill Tarter. Yes. On her right, Michael Russell, geochemist, interested in how life on Earth got started some 4 billion years ago. Michael predicted the discovery of a kind of submarine hydrothermal vent later discovered in the North Atlantic at the so-called Lost City site, and argues that similar geological and geochemical processes occurring 4 billion years ago in the Earth's oceans may have formed life's first organic molecules and metabolic pathways. Since 2006, Michael has been working as a senior research fellow at NASA's Jet Propulsion Laboratory in Pasadena. Welcome, Michael, too. On his right, Dave Charbonneau, astronomer. He is a celestial detective. He hunts for Earth-sized exoplanets outside our solar system that could harbor life. Last year, he used a group of small ground-based telescopes to locate a watery super-Earth just 40 light-years away. Dave also uses space-based telescopes to characterize these mysterious planets and is a member of the science team using the Kepler Space Telescope to search for exoplanets. He is professor of astronomy at Harvard and an astronomer at the Harvard-Smithsonian Center for Astrophysics. Welcome, Dave, here too. And finally, here on my left, Steven Squyres, planetary scientist, a veteran of several NASA planetary exploration missions, best known for his role as scientist in charge of Spirit and Opportunity, those hardy little robots who have been combing the surface of Mars as part of the rover mission. Steve's main research areas are the history and distribution of water on Mars and the possible existence of a liquid water ocean on Europa, one of Jupiter's moons. He is the Goldwin Smith Professor of Astronomy at Cornell University. Could we welcome Steve as well? Now, ladies and gentlemen, our program is going to be really in two parts this evening. In the first part, I'm going to talk to each panelist in turn about the different ways they are using to search for life and also for the origins of life. During this part of the program, we are going to be really entertained because they're going to share, and I've seen some of them already, some great images about the work that they do, and that's really very exciting. We are also very privileged this evening because we're going to hear some completely new news released by NASA only this afternoon about an exciting discovery which has just been released from the Mars Rover Spirit. So we have to look forward to that. Now, once we're all up to speed about what different approaches are being used, we're then going to have a more general group discussion between all of us, all the panelists, about the search for life in the universe. So that's what we have on offer for you, and it's going to be a great evening. You're going to have a good time. Just believe me, you're going to have a good time. Can I start with you, Steve?
Yeah.
Now, you've been in charge of these two robots wandering around Mars for quite some time now. I mean, they were originally only supposed to be for 90 days. So what on earth have you been doing for the last 3 or 4 years after those 90 days?
6.5. But today is actually day 2,281 of our 90-day mission. So, yeah,
You're not a detail person, are you? No?
Yeah, a little bit. You have to be in this job. No, they're doing real well. Both rovers are still up there. Both are still returning data. And as you said, we actually had a paper published in Science today announcing what I think is a pretty significant discovery from one of the rovers. So they're still going.
Well, I think we've got to know, what is it? What have they discovered?
Well, all right,
today?
so
Come
we can
on,
go
tell
right
us.
to that picture if you want. There's a picture which I hope we can put up in a few minutes here. Not that, but...
oh, well, what is it? Is this what it looks like? This may be what it looks like.
So that's Spirit. That's Spirit in the foreground, all tricked out and ready to go to Mars. I'm the good-looking guy in the white suit.
Why did you call it Spirit, by the way?
The names were actually picked as part of a NASA outreach activity where children suggested names for the rovers. And the names Spirit and Opportunity were suggested by an 8-year-old girl from Arizona named Sophie Collis, who had been born in Russia and raised in an orphanage and then came to the United States. A very touching story. Anyway, so that's Spirit, looking really clean. Doesn't look like that anymore. Opportunity is against the far wall there. That picture was taken at Cape Canaveral in Florida about 7 years ago, right before we launched.
And the discovery, what's it discovered?
Yeah, okay, what we have discovered is in some outcrops of rock that were explored 4 years ago by the rover Spirit, we have found carbonate rocks. Now, carbonates are particularly important on Mars for the following reason. Carbonates are rocks that typically precipitate from water. Okay, and water is an essential ingredient, we think, for life. Now, we have found rocks that have precipitated from water on Mars before. We found sulfates, we found other things, but these are all rocks that formed under very acid conditions. You know, people have tried to describe the results of our mission as water on Mars, water on Mars. Until now, it was mostly sulfuric acid on Mars. Now, there are organisms that can exist in acid conditions, but they're very tough, very hardy, very unusual. The thing about carbonates is, carbonate rocks will dissolve in acid. Okay, these point to conditions that were more neutral, more normal water, more friendly to life. So of all the discoveries that the rovers have made over the 6.5 years that they've been on Mars, I think this one points towards a more life-friendly set of conditions than anything else that we've seen to date.
Do you have any idea how old they are?
Oh man, I wish I did. Everybody always wants to know that. They're certainly very old. They date from, I would say it has to be, say, the first billion or so years of Martian history. So they're extremely ancient rocks. But the only way that you can really put a date on rocks is by actually bringing them back and putting them into a laboratory, and we don't have that capability yet. Yeah, there's the outcrop. It's called Comanche. This is a false color image, so it's not quite that blue. But it's strange, strange stuff. It's not like anything we've ever seen before.
And have you found any other evidence in the last 6 years that would support the notion that there was water on Mars?
We found a lot of evidence for life. We can flip through a few pictures here, and I can show you some of them. Really, really nice evidence in a number of forms. One of the most significant was found by the Spirit rover when we were dragging the wheel of the rover through some soil. After about 800 days of driving around, this rover that was designed to last for 90 days, the right front wheel seized up. And so now when we drive Spirit, we have to drive backwards and we drag the wheel through the soil. But what we've discovered, there's a little silver lining to that, because what that wheel does is it digs this marvelous hundreds of meters long trench through the Martian soil.
Is this an example?
Yeah,
is this white thing an example?
Yeah. And one day, the soil in the trench popped up as bright as white snow. We'd never seen that before. So we whip out our spectrometers and we take a measurement. And it turns out that stuff is 91% pure silica, SiO2. Now, it's not quartz. It's not crystalline silica. This is not beach sand. This is essentially opal. This is like the kind of thing that you can form in volcanic vents, in hydrothermal systems, that sort of thing. So this points to an ancient hydrothermal conditions that were more acid as opposed to the conditions that we see from the carbonates.
So that's why the carbonate is so important.
That's why I think the carbonate's
pH.
significant, is it points towards what would have been, I think, more favorable conditions for life, yeah.
What else do you hope you might find if they keep going, if it keeps going a few more
that's a hard question to answer, because nothing that we've, I mean, I didn't expect this. There was another thing that we found. In fact, I think it's the next picture that comes up here. At the Opportunity landing site, we landed, and the first thing we see sitting in the soil, this is a picture that was taken with our microscope. It's only 3 centimeters across. And the surface of Mars at this place is littered with an uncountable number of little round things. And they're 4, 5, 6 millimeters in diameter, and they're everywhere. What we eventually realized was that these are actually what geologists call concretions. Concretions form typically in sedimentary rocks on Earth that are saturated with liquid water. There's some mineral in them that wants to precipitate out. And it starts to do that. And it nucleates, and it starts to grow and adds layer upon layer, making a little hard spherical nodule. It's kind of like the way an oyster builds a pearl. And there are just bazillions of these things at this site. So what this is saying is that the water once soaked the ground here. I never in a million years would have predicted this. So if you ask me, what do I hope to find? I don't know, more cool stuff.
Well, talking about cool places, I guess we could go further out into the solar system.
Yeah.
Think about Europa, maybe.
Actually, why don't we talk about just this thing real quick before we go on to
Europa?
Yeah,
no, sure.
I want to hit on this, because this gets to the possible future of Mars exploration. A fascinating discovery that has been made just in the last, 5 years or so, is that there's methane in the atmosphere of Mars. Now, the thing that's weird about that is that methane is a molecule that will only last for a very short time in the Martian atmosphere. The Martian atmosphere is bombarded by ultraviolet radiation from the sun. It's going to bust up those methane molecules, and they're going to last a very short time. So if you see it in the atmosphere, there has to be an active source on the surface somewhere. So what produces methane? Okay, cows produce methane. It's probably not cows. Volcanoes can produce methane. Microbes can produce methane. So what this is saying is that Mars is either a volcanically active world or a biologically active world, or both. We don't know, but we're hoping to send a spacecraft to orbit Mars to look at the methane in more detail, figure out where the sources are, and maybe understand better where it comes from.
Biology, but no cows.
Probably no cows. I would be surprised, because if there were cows, we already would have seen them from orbit, so I feel pretty good about that one. All right, now, the next thing you mentioned was Europa. Okay, getting further out in the solar system. You know, if I could figure out how to do a mission to answer the questions on this world, I wouldn't be screwing around with rovers on Mars. To me, this is the most fascinating place in the solar system besides Earth. It's a moon of Jupiter. It has a crust of ice, but there's strong evidence, no smoking gun yet, but really powerful evidence that beneath that crust of ice lies an ocean of liquid water. We can go to the next picture. It actually shows a close-up of what the crust of Europa looks like, and it looks just startlingly like what you see when you look at sea ice on the Earth. It's not hard to believe that there's water underneath that, and there's a lot of good evidence to suggest it as well. The thing that's interesting about that, and we're going to hear more about this later, there are places on the Earth's seafloor where geothermal activity, volcanic activity from the Earth's seafloor, provides energy that organisms can use to drive their metabolisms and form the base of this incredible local food chain that you find at deep-sea hydrothermal vents on Earth. So it's entirely possible that if there's an ocean of liquid water on Europa, as we believe there is, there could be life that derives its metabolic energy from the internal geophysical heat from inside of Europa. So I think it's a fascinating place to try to go and do a mission, but you know, I know how to do Mars rovers. I don't know how to do submarines on Europa. That's a tough one.
Is it the geothermal activity that keeps it liquid so far out?
Yeah, it is. It is. Essentially what happens, the mechanism that keeps Europa partially molten, it's heating by tidal deformation. What happens is Europa's in orbit around Jupiter. Because it's so close to Jupiter, this massive body, it's distorted. It's not spherical. It's got kind of a big tidal bulge. But its orbit is not perfectly circular. It's elliptical. And so sometimes Europa is a little closer to Jupiter, sometimes a little further away. And as it's closer, the tidal bulge is bigger. When it's further away, it's smaller. And so it's getting flexed back and forth. And if you can take like a piece of wire, like a coat hanger wire or something, bend it back and forth real fast and put your fingers on the bend, it'll feel hot. That's what's happening. Europa's getting flexed back and forth, and it heats it, melts the interior, provides potentially a source of energy for life.
So if President Obama gave you an infinite number of dollars...
Oh, that would be nice.
How would you design, what sort of probe would you design for Europa?
All right, the way you would want to do Europa, I'd want to do it in at least 2 steps. The first thing you want to do is send an orbiter with maybe a deep-sounding radar that can look through the ice and find where the thin spots are. Because it's probably not uniform. Okay, and if I got to get through that ice, it's kilometers thick. I want to know where the thinnest spots are. That's the first mission. Second mission, you go for it. Second mission, you go to the surface, and then you would want to have some kind of probe that has a heat source, probably nuclear, in its nose that can melt its way down through what might be kilometers of ice, and then when it gets to the bottom, and it's deploying a data cable behind it, when it gets to the bottom, part of it swims away, a free-swimming, autonomous robotic vehicle that can then swim through Europa's oceans, transmit data back and out, and back to Earth. It's a really hard mission. It's a really hard mission.
I'll write him a letter. Just
yeah, you do that, please.
Okay, thank you, Steve. We'll come back to you a little later. Dave Charbonneau. I remember only a few years... Oh.
That's how you got there.
Is this it?
You want to do this?
Yeah, do it.
This is how we landed on Mars. You hit the top of the Martian atmosphere going about Mach 27, 27 times the speed of sound. We throw out a supersonic parachute at Mach 2. That hurts. 18 Gs when you put that out. We don't drift down lazily on a parachute on Mars. The atmosphere is very thin. We drop the heat shield. We lower the lander. That's the lander there. It's got the rover all tucked up inside of it. We're still screaming down towards the surface about 300 kilometers an hour. We inflate airbags. Like the airbags in your car, except a lot more expensive. Cut them free. They drop to the surface, and we bounce. And we bounce. And we bounce. And we do that for like 10 minutes and about a kilometer before the thing comes to rest. Inflate the airbags, open up the lander, and then fold it up inside as the rover, which now has to kind of unfold itself. It has to do origami in reverse to turn itself into a rover. I mean, watch what the wheels do here. Watch this. I mean, I still get the heebie-jeebies watching that 6.5 years later. Once it's all unfolded, we take a panorama. We did this so upside down when we drove off the lander. And then you go monster trucking down onto the Martian surface, and off you go. And 6.5 years later, they're still going.
Good for it. I think we should give it a clap. Dave, I just remember it seems only a few years ago that one of the questions was, could we ever see a planet going around a star? Now I think there's over 400 of them. I mean, what's happened in the last 10, 15 years? How have we discovered all those exoplanets?
Yeah, it's been a really a remarkable time to be alive if you're interested in planets orbiting other stars, and that's the big news. You know, I think it's helpful to pause for a moment and look back through human history. If you go back 500 years, and there's written records, and there's this thinking about if the points of light in the night sky really were stars, maybe they would have planets. And if you go back even further to the times of the Greeks, you can see this yearning for coming into contact with other worlds. They didn't have an understanding of where those worlds would be, but it's this very human sentiment. And we're all alive at this magical moment when we just happen to have the technological ability to actually find those planets orbiting other stars. And it started in 1995, and it's been skyrocketing ever since. There's really there's two methods by which astronomers have been able to find planets in large numbers around other stars. And they're both a little subtle. We don't go and take photographs. Unfortunately, we're not going to be able to send probes. I wish we could. It's all through remote sensing. One is what we call the wobble method. And my guess is that this has been so successful that many members of the audience have already heard of the wobble method. And the idea there is, you might imagine that, probably in school you were taught that planets just orbit around stars like that. But actually the two do-si-do in a dance. It's just that one of the dance partners is 1,000 times heavier than the other dance partner. But if you could only see that one heavier dance partner, which is the star in this case, and you could look very carefully, you would see that the star is actually going back and forth, coming towards you and away from you and towards you and away from you. And you would know that there was something in orbit around that star, and you'd be able to measure its mass. Okay? And that's our first clue about how we'd find planets orbiting other stars.
And how would you measure them going backwards and forwards? I mean, how would you know that was happening?
You would be able to measure the change in the speed of the star. So if you look very carefully at the light of the star, you would measure what we call the Doppler
It's
shift.
a Doppler effect.
And it's the same effect, if you hear, I've been in New York City now for all of 6 hours. There's been a couple police sirens. And, and it's coming towards you.
Just two. Yeah.
Yes, when it's coming towards you, you hear a higher pitch, and when it's going away, you hear a lower pitch. The exact same thing happens with light, which is another wave. And that's how we can find planets orbiting other stars. The other method, and the one that I think is more promising when it comes to finding Earth-like planets, is what we call the transit method. And the transit method, I think we've got a nice movie just to really illustrate the transit method. The idea behind the transit method is very simple. Is you just want to measure the brightness of a star very carefully, and then what you might observe is that every time that a planet passes in front of the star from her point of view, if you're lucky enough that your line of sight goes through the orbital plane of the planet, you'll see the star appear to get fainter, as shown here. And then when the planet finishes transiting the disk of the star will brighten up, and you'll see that happen again and again. And why that's so special is the depth of that eclipse tells you the size of the planet. So if you put them both together, if you've got the wobble, which tells you the mass, and the transit, which tells you the size, then for the first time, you can calculate a density. And that's your first clue about what that planet is made of.
Does that limit the size of a planet that you can detect? How small a planet compared with the star it's going around do you think you can detect?
Yeah, that's a great question. If you were hoping to use a backyard telescope to do this, and you may not anticipate this answer, the answer is you could do it. Okay, from the ground, you could actually measure the change in the brightness of a star at the level of about 1%. The star would get fainter by about 1%. And actually, if a Jupiter-like planet goes in front of a star the size of the sun, it blocks 1% of the light. And actually, most of the transiting planets we know about have been found with small ground-based telescopes that I can put in my carry-on luggage, some of the smallest ones. It's really remarkable, okay? And so if you were a backyard astronomer, you could actually do this if the skies cooperated here. However, if you want to find planets that might have life, then we're talking about small rocky planets. Of course, that's much more difficult. So for a star like the sun, a planet the size of the Earth was 100 times fainter yet. So it only blocks 1 part in 10,000. And for that, you have to go to space. And so NASA has gone to space because that question is so exciting to us. And that's called the NASA Kepler mission. And I think we have a movie showing the location of the field of regard of the NASA Kepler mission. What's good to know is that actually this field, this group of stars, is observable to you. It's overhead. You can see it from New York City during the summer months. And it's in the constellations of Cygnus and Lyra near the bright star of Vega, which even through local skies you could probably see. And so what Kepler is going to do is it's going to stare at 100,000 stars, and most of them are going to be boring, boring, boring. But a small fraction of them will show these periodic little eclipses. And we'll say, oh, there's a planet, and here's what we think its size is based on how much light is blocked. Of course, if you want to find planets like the Earth, they only go around once a year, and so you have to be very patient. Kepler just launched last year, but this signal only happens once a year, and so you'd have to wait 3 or 4 years to see enough of these signals to really believe it. But this is happening now, and so it really could be. And I'm a member of the Kepler team, and Jill Tarter is a member of the Kepler team. Kepler is performing as designed, and so if those planets are out there, we should be finding out about them pretty soon.
How big? Tell us a bit about Kepler. It's got a big mirror, has it, or how does it work?
Yeah, well, Kepler is basically the main mirror of Kepler is about 1 meter, so it's about that big. And then on the front, there's a big lens. So there's a big lens and a big mirror, and basically it focuses the light from these 100,000 stars onto basically the world's best digital camera, okay? Mm-hmm. And so we don't have an image of the digital camera, but it's the actual camera would be about this big. It's a truly remarkable engineering feat. And then it's a very simple measurement in principle, which is that you're just, for every single one of those stars, every 30 minutes, you're just measuring the brightness and measuring the brightness and looking for that special moment when one star out of 100,000 gets a little bit fainter, and then it repeats, and that only lasts maybe 10 hours, and then nothing for another 12 months, and then it happens again.
So that's a lot smaller than Hubble, for example.
It's a smaller mirror than Hubble, yeah. The telescope can watch many more stars simultaneously. Hubble can really only look at one at a time.
And so if you're going to have an Earth-like planet, that presumably has to be quite some way away from the sun that it's circling, from the star. So does that mean we really do have to have a time scale of 1, 2, 3 years? Is that really what you've got to aim at?
I think it is if you are obsessed. You know, we grew up around a certain kind of star. And if you think that stars like the sun are the best bets for finding planets like the Earth with life on them, then yeah, there's no getting around the fact that basically the temperatures of the planets in our solar system, if the planetary scientists will excuse me, are largely set by the distance that they are from their stars. And the time it takes for a planet to go around its star, that's determined by the distance. So there's no getting around the fact that if you want habitable planets around sun-like stars, you just have to look for these one-year orbits. However, as it turns out, most stars in the galaxy are not like the sun. If the sun is like a 1,000-watt light bulb, most stars in the galaxy are 1-watt light bulbs. They're Christmas tree lights. And so if they form planets just like the sun, then those planets are going to be a lot easier to find, but you have to look very, very close. And so instead of going around once a year, they go around once a week. And what's so exciting is because the star is small, you don't need to go to space. You can actually do this from the ground. And so that's actually what I've been busy doing for the last few years is building arrays of telescopes from the ground to look for these Earth-like planets orbiting very different kinds of stars.
So could you guesstimate for us, I mean, given what's been seen already and how many stars have shown evidence of planets, how many planets that might be suitable for life are out there?
Oh. Well,
you can say a lot if that's easy.
Yes, I think it's fair to say that when we only knew about our own planetary system, we thought all the other stars in the galaxy would have systems of planets just like our own. Was that because we were good scientists or good predictors? No, we were myopic. And we had grown up under a certain set of conditions, and then for hundreds of years we'd worked out theories to convince ourselves that of course it had to be the case. Now, predicting the architectures of planets orbiting other stars is surely an easier task than predicting whether those planets actually have life. And we didn't get the first part right. So what I'm saying is at this point we have no ability to pontificate about what fraction of stars in the galaxy have planets like the Earth that actually might be habitable, have liquid water. But to give a number, there are something like 100 billion stars in the galaxy. So even if the occurrence of life is very rare, there still could be many systems to look at. And I just wanted to show this one movie of our Mirth array, which actually shows a hunt for very, very nearby stars. Like I said, you know, these low-mass stars, what we call M-dwarfs, they outnumber us 10 to 1. You probably were told in school that you grew up around an average star. That's totally false. Our star is much, much bigger and brighter than most stars in the galaxy. But because those stars are small, you can see a small planet going in front of them. And so this movie shows a search that we're conducting in Arizona with 16-inch telescopes. And if we find planets orbiting those stars, we actually would be able to to maybe even go further and ask whether they actually are inhabited.
So can you do even more than that? Can you tell something about what those planets are like and whether they're likely to be suitable for life? Have you got ways of doing that?
Yeah, I think that's really the big question that we're looking forward to right now. We're just at this magical moment where for the first time, because of the Kepler mission and because of this project, which we call Mirth, because we're looking for Earth-like planets around M dwarfs, and we pronounce it Mirth because it makes us happy. Because those projects have just gotten going, we have the first moment in history where we can actually find planets. But of course, that doesn't tell us whether there actually is life on those planets, just that they're like the Earth. Okay. And yeah.
I just want to jump in with one thing about this habitable zone thing. I think the situation's even better than the story that you're telling. Because, I mean, the story that you're telling is kind of a Goldilocks thing where here it's too cold and here it's too warm and here it's just right. But one of the things that we've learned from studying our solar system is that, I take Europa as an example.
Yeah.
I mean, Earth lies in the habitable zone and Europa lies out of your notional habitable zone, and yet the internal heat could actually produce a fairly habitable environment inside that. So I think the story's even better than the one you're telling.
So there's more environments
around
around
I think that the
stars.
habitable zone is a lot bigger than the Goldilocks story. I think there's more stuff out there.
Yeah, I think that's a great point. So even in this restricted case, we may be underestimating the environments around stars that actually allow planets.
And can we detect those? I mean, are there indicators that you can find from Earth that would say these are good candidates?
Yeah, that's what really I think unites us as a panel, is the different approaches we bring to thinking about that particular question. So my answer as an astronomer is that there are that life so dominated the surface of the Earth that it completely changed the chemistry of the atmosphere. And that's something we can study remotely. When you find a planet orbiting another star, astronomers have come up with methods to study the chemical content of the atmosphere, okay? And so it's that inadvertent, inevitable consequence of life on the surface reflected in the chemistry of the atmosphere that we can study remotely.
How can you detect the chemistry of something so far away? How can you do that?
Well, what you do is you find a planet that goes in front of a star, which of course is the whole design here.
Yep.
And so I think it's good to mention a bit of history. I'm showing here an image of Venus in front of the sun. And I don't know if anyone saw this. This happens very rarely. It will happen in 2012 and then not again for another 130 years.
But it happened a few years ago.
And it happened a few years
I saw
ago.
this from New York, actually.
Oh, you did?
Yeah.
Yeah. So 250 years ago, a very observant Russian scientist by the name of Lomonosov looked carefully, and if we go to the next image, he looked carefully when Venus was just getting close to the limb of the sun. And what fascinated him was that the outer limb of Venus was bright. And what he inferred is that Venus, like the Earth, has an atmosphere, and you're seeing light refracted through that atmosphere. And so he was the first person to infer that planets other than the Earth had atmospheres, and he was right. It was a remarkable inference. That's the exact same method we're talking about when it comes to studying the atmospheres of planets orbiting other stars. We wait for them to go in front, and then we use the star like a flashlight. Some of the light goes through the outer parts of the atmosphere, and imprinted on that's the fingerprint of the chemical content of the atmosphere. And if we see things like molecular oxygen, methane, water, and then we also know that the temperature and the composition are similar to the Earth, then that's the argument you build that maybe the best explanation is that there's life.
And your instruments have the sensitivity to see that light years away? I mean, this is obviously only tens of millions of miles away.
Yeah, no, the Hubble Space Telescope has already detected the presence of water and methane and atoms like sodium and hydrogen in the atmospheres of planets orbiting other stars. That's done. That's old news. But it's gas giants. Those are big planets, which are easier targets.
Yeah.
To get down to these truly small rocky planets, I think if we can find planets orbiting small stars, because the favorable contrast ratio of having turned down the brightness of the star, you can do it with the James Webb Space Telescope, which I should mention that a model of the James Webb Space Telescope is actually on display in Battery Park, and I think there'll be even some stargazing there Saturday night. So I think we could do it with that instrument, but then again, maybe those kinds of stars don't make planets like the Earth.
And what's special about that space telescope? How does that
It's
differ
bigger.
from Kepler? Just bigger.
It's more powerful, and it also works at infrared wavelengths. And so it looks at longer wavelengths of light beyond the visible spectrum. And that's where these molecules are the most, that really show
So
off
it's
their
particularly
fingerprint.
sensitive to the spectroscopic
It's the chemical
indicators.
fingerprint
Yeah.
of
Yeah.
molecules, and it's those molecules that reveal life.
Okay, I think move on to Mike. We've been talking about looking for life on other planets, but we could get clues about how life first emerged on this planet, because we know it actually happened. So how do you think, how did life begin here on planet Earth?
So this is my favorite planet, I have to say, and can we just have a slide, please? It was a water world. No, the one before this. This was a water world, so it's a very different planet. This is ours, but it was a third of the age of the universe ago. It was completely covered in water. It was an extremely rough place to be. Many people might have heard of Darwin's warm little pond. There is no place on this planet for Darwin's warm little pond. It's being impacted with meteorites, ultraviolet radiation, about 10 times as much as today's. You can see that it's extremely stormy. There's not a Florida to stop the hurricanes. You have the roaring 40s, so to speak, going all the way around the planet. It's a very violent place. There's nothing at the surface that will help us to give us an understanding of life. But one way we can think about this planet is it's rather like an organism. And I'm not talking Gaia here. I'm saying, what does this kind of organism do? If we thought of it as an organism. We heard Steve talk about the generation of methane on Mars, and Steve wasn't too sure, none of us are, what's the source of that methane? Now, it could easily be inorganic. It's likely to be inorganic. In other words, because there's carbon dioxide on Mars, and as it interacts with the surface of Mars, then the carbon dioxide gets reduced to methane. But also methanogens, archaebacteria, actually produce methane as well. So hence the problem. But if we think of this planet rather like a methanogen, that it actually is going to produce methane, why? Because it's surrounded by carbon dioxide. From our point of view, this planet is pretty oxidized. It's got carbon dioxide and water on the outside. It hasn't got any oxygen, of course, because that's related to photosynthesis. But this planet, we could
So you can only get oxygen from plants. I mean,
yes,
at this
effectively
stage
only
of
from plants.
you can't get any oxygen. Yeah?
That's right.
Yeah.
So this planet is emitting methane, and what we would suggest is that what life does is to quicken those reactions. So in other words, life has a job to do, and that's the way we should think about it. We shouldn't say, what is life? That is definitely the wrong question. What we should ask is, what does life do? So, and if we ask that, then of course what it does, if you think about it, it takes carbon dioxide from the atmosphere and reacts it with hydrogen from water to make a small but ever continuous number of organic molecules. That's life's job, if you like. And that's the way I think we were talking about, the way we might be able to see it. Now, if we think about Venus, Mars, and the Earth, they have similar carbon dioxide, or did have similar carbon dioxide to nitrogen ratios. So in other words, they were all possible places for life to start. Of course, Venus got too hot. We can't tell whether there was life there or not. Mars seems to have been a likely place to have had life on at some time, but of course there's a detection limit problem about whether we could find it on Mars. But nevertheless, this is the kind of place that any water world like this, with a rocky interior, I would say, would have life. One more thing about this, and to say, why can one be so confident about this? Well, we know that this was a very hot planet. I mean, it's still pretty hot in the interior, 5,000 to 6,000 degrees centigrade. And how does it get rid of its heat? It gets rid of its heat by convection. Convection in the core, which gives us the Van Allen belts and so on, that actually protects us from cosmic radiation. Convection in the mantle of the planet, convection in the crust, giving us hydrothermal systems, and convection in the atmosphere, and so forth. Now, the paradox of convection is it actually makes chemicals into disequilibrium. So you get a chemical potential generated because of convection. So convection satisfies the thermal potential, and then along comes convection near the surface, and we get this potential between hydrogen from the planet, so it is emanating some hydrogen, and at high temperature it emanates carbon dioxide, and what life does is it reacts the two together to make to start with, either methane or acetic acid. And my particular pitch for Mars would be to say, well, maybe the best chance for looking for life on Mars is, of course, to look for waste products, and that waste product might well be acetic acid because methane is too ambiguous.
So I think, are you sort of arguing that chemical potential is you've got to think about that in terms of producing the energy for life that it could utilize? Is that,
exactly.
Is that a cornerstone of the argument?
Exactly. So in other words, just like lightning is related to the discharge of energy in clouds and so forth, and by the way, probably cosmic radiation is what helps the lightning strike. If we have the next slide, I can show you that we would say that this is the kind of system, this is called Lost City. It's 600 meters deep in the North Atlantic, and we would say this is the best place for life to have discharged its energy on the early Earth. Because here, this system generates hydrogen, large quantities of hydrogen, some methane, as these things keep doing. We still don't know the real source of that methane because, of course, the Earth can produce methane geochemically, and also a little bit of acetate from acetogenic bacteria in this kind of system. So this Lost City system, we would say, is the kind of reactor, the natural chemical reactor. In fact, my preferred word is this kind of system, which we predicted on the basis of this hypothesis, is the kind of hatchery of life. Because this is where we have chemical disequilibrium. We have gradients acting across. We've got a thermal gradient between the hot interior and the cold outside. On the early Earth, just like we've been hearing from Steve about Mars, there was probably an acidic ocean. So we've got protons trying to get through the outside of the margins of this inorganic precipitate. And those are the kind of systems that kind of kick life into being, we would say. Life needs a bit of help. Carbon dioxide and hydrogen don't like to react. Well, you probably know even hydrogen and oxygen don't react unless you strike the match. You could say that life is what strikes the match between carbon dioxide and hydrogen to make organic molecules and water. So those, and the two first effluents would have been acetic acid or vinegar by the so-called acetogenic bacteria and the methanogens generating methane.
So what sort of life could live in these, well, they seem quite peculiar environments. What could get on in that sort of environment?
Well, that's such a good question. Perhaps the next slide for this one. Now, when these are black smokers, and I think most of you have seen black smoke. One back, please. Most of you have seen black smokers. The blacks, this is 400 degrees centigrade, this water. It's hotter than anything in the oven. Of course, so it would boil, it would destroy any organic molecules, but you can see that life is pretty happy there. There's even a crab living there in the kind of safety of the cooler regions. This is pretty interesting, though, because it brings metals into the ocean. On the early Earth, as on any sunny, wet, rocky planet, by the way, those metals would have gone straight into the ocean. Those metals are iron, zinc, cobalt, nickel. We still buy those if we need them from chemist shops. These are all important metals for the way life works. There's a beautiful phrase by David Garner, and he says, it's the inorganic elements that bring organic chemistry to life. It's the inorganic elements that bring organic chemistry to life. And I would say, right at the beginning, when there were no organic molecules on the planet, the first membranes, the first compartments were all inorganic. Probably silica, maybe some iron carbonate, and some iron and nickel sulfides acting as catalysts to allow the reaction. And that came from here, but life didn't start there. And if we go to the next slide, please. Then here's the rainbow pool at Yellowstone, and the tendency is to say that these bacteria, for example, an archaea, there's an archaea that on the bottom left of the diagram there, perhaps lives about 60 degrees centigrade.
An archaea is a sort of bacteria?
It's a kind of, well, it's what's called a prokaryote. The three dominions of life. Basically, there's the archaea and the bacteria, which are very similar to each other to look at, although very different when you look at them carefully. And there's us, of course, which is actually probably symbiosis, endosymbiosis between the two. The two then came together to give us. But if I can get back to this, the assumption is that that anything that lives in that pool is an extremophile because we wouldn't want to live at 60 degrees centigrade. But actually, somebody called Harvey in 1924 suggested that life might have started in hydrothermal systems. A wonderful paper in Science because he said there was so much iron and sulfur there that life might have started there. Now, there are extremophiles in this picture, and you can see this kind of carrot-looking material, and here's a carotenoid, and it just is colored like carrot. And what it is, it's a kind of defensive molecule against solar energy. So actually, I would say these kind of reddish molecules here, these reddish bacteria, and next slide, please, and even things like cyanobacteria and grass and trees, to me, they're extremophiles. And of course, we are extremely extremophile. But we've tended to think of it from our point of view that everything like us is normal and everything out there is extreme. I would look at it the other way around.
Michael, this is my last question, but it's really difficult, really difficult. Even so, archaea, they're very complicated. How did that come about? How could you get that complexity?
Well, the first thing is, if we take an analogy of a car, then we know we've got to have 4 wheels and we've got to have a vehicle. And the first thing is we've got to have an engine. Eventually, of course, we can get sophisticated and we can have a regulator like a computer. But in the analogy, the engine is the metabolism. So first of all, you had to have a vehicle. To us, that's a compartment, and that a vehicle, the engine was driven by the fuel of hydrogen and carbon dioxide and protons, so that gives us the engine, and that gives us reproduction because these bubbling waters can give us bubble after bubble after bubble of this material. And then, of course, along comes RNA. Now, RNA doesn't just come along. I mean, for example, all the kind of walks of life, we know that bureaucrats couldn't have been there in the hunter-gatherer society. Everybody had a job to do in hunter-gatherer society, and I would say exactly the same of life. You can't have an RNA come in and DNA starting to boss around metabolism. What actually happened was that these things like adenosine triphosphate, at ATP, you make your body weight every day of ATP, is one of an RNA or a DNA molecule. If you have that, then, in other words, ATP is doing a job. And what happened was these coenzymes then eventually probably could reproduce each other, NADP and FAD and so forth, and ADP. They could probably reproduce each other, and eventually they strung themselves out into making RNA. And I admit that that's a huge jump. But the thing is, if you think of it as a chasm, the geochemists are on this side of the chasm, and the microbiologists, evolutionists are on the other side of the chasm. They're not over there or over there, and we are trying to kind of make the links, of course. And I'm fairly confident.
Okay, thank you, Michael. Now, Jill. Search for extraterrestrial intelligence, 50 years. What is it you're looking for? I mean, what is it that would be a signature of extraterrestrial life?
Well, 50 years, people keep asking. You've been looking for 50 years. You haven't found anything, right? If we had found something, you'd all know about it. You need to think about that. Here's the analogy. We've been using other people's telescopes, so we haven't been looking very much at that 50 years. And all of the searching we've done to date is like taking a single glass of water, 8 ounces, out of the Earth's oceans, and looking in that glass and saying, are there any fish there? Are there any fish in the ocean? Well, there are no fish in my glass, so probably there aren't any fish in the ocean. That's the kind of level of silliness when you say that 50 years of searching has any significance. So what we're doing is we're building a brand new telescope, right? And I think we've got a video of that. Right. So we spent 3 years doing the R&D to figure out how to do it. We spent 2 years actually building this in Northern California. Today we have 42 of these antennas working as a telescope, doing radio astronomy and SETI simultaneously 24/7. And this is the future that we see for the Hat Creek Valley in Northern California, where this array will grow from 42 to 350. Now, to make that happen, you just have to add money, right? We're ready. So anybody who brought their checkbook tonight, I'd be willing to entertain that. And inside these telescopes, there's an amazing amount of innovation to be able to do things that we haven't done before. I think there's a still that shows what we call a feed. And you can basically think of this funny Buck Rogers sort of death ray as being the aerial on your car. It captures the radio waves that are focused by these funny-looking telescopes. So the next picture, I mean, perhaps only a mother could love telescopes that look like that, but in fact, I do love them, and they're doing a fantastic job. And so you ask me, what is it that we're looking for? Well, we're looking for something that, as far as we know, nature can't produce. So we've heard about looking for signatures of habitable worlds. We've talked a little bit about looking for biosignatures on those worlds. What we're doing in SETI, both in the radio here, which is what I work on, and also in the optical part of the spectrum, we're looking for technosignatures. We're looking for something that is engineered. So let's show the next slide. This is a radio picture of the most distant object that we've ever manufactured. And this is a signal from that object. It's the Voyager 1 spacecraft. It's 106 times as far away from us as the sun is. It's out at the edge of the solar system. It's about to go into the interstellar medium. And I'm talking here so that you can look at this diagram, and frequency is displayed horizontally and time is displayed vertically. And do you see it yet? How about there? Right? And in fact, it's no problem at all for our signal detection algorithms, our computers, to find these kinds of patterns. We're looking for things that show up at a very small range of frequencies. Nature produces signals that cover a lot of the spectrum. So here in the radio, we're looking for frequency compression. In the optical, when we look for signals, we look for time compression. We look for bright flashes that last a billionth of a second or less. That might be somebody's laser that's being focused by a big telescope and sent in our direction. Or it might be some new astrophysics that we don't know about yet. So these are the two ways we're looking today. We think that makes sense. We think that's consistent with what we know about the universe and the electromagnetic spectrum. But we could be wrong. We might be looking for the wrong thing. Any technology out there is going to be older than us, or they're undetectable. We've had technology for maybe 100 years that could be appropriate to interstellar communication. Our galaxy's 10 billion years old. So we don't know if there are any other technologies out there, but we can be fairly confident in saying that we are the youngest. Any other technology that's there and detectable is going to be older. So they might be doing something totally different. They might be using zeta rays. I don't know what a zeta ray is, but I wouldn't be surprised if there's some physics yet to be understood and some technologies yet to be discovered and invented. And maybe zeta rays is one of those things. So what do? You do what you can. You use the tools that you have at hand. I mean, Columbus didn't wait for a 747 to get across the ocean. And so you just try and stick around long enough to get smart enough to invent these technologies, and then you start using those in the search, as well as the radio and the optical. I mean, it may be that some advanced technology has an Institute of Ancient Instruments that they keep just for the purpose of trying to attract the attention of the emerging civilizations such as we are. So that's what we're doing. And the fun thing, Dave talked about what a great time to be alive. I got hooked on SETI in the 70s when I realized that we, as a species, have been asking this "are we alone" question for millennia. And what did we do? We asked the priests or the philosophers or whoever we thought was wise And we asked them, what should we believe? But actually, in the middle of the 20th century, we got some new tools, radio telescopes. And so I got hooked on SETI when I realized that I was in the first generation of people who could try and do an experiment to answer this old question, rather than asking, what should we believe?
Tell me about how difficult is it to be sure you're looking at something natural or unnatural? That must be quite difficult sometimes, I guess.
Well, if you looked at a star or a galaxy or a molecular cloud with this type of instrument that we've built, it would mostly look like all that snow in the background there. We have built instruments, what we call matched filters. They're really, really good at finding this particular set of signals that we've defined. But as I've already said, we may be looking for the wrong thing, or we may be using the right technology, but looking for the wrong kind of signal. And so the great thing is that not only do we have tools, but they're getting better every day. This is all about computing. We can build a giant radio telescope out of lots of little pieces, and you can build an array of planet hunting telescopes because we can connect them with a lot of computing. And that computing is getting exponentially better. So Frank Drake, in 1960, did the first radio search, looking at 2 stars with a spectrometer that had 1 channel. Today, I look at multiple stars with spectrometers that have hundreds of millions of channels. And in fact, the tools I use today are 14 orders of magnitude, 14 factors of 10, more comprehensive than what we started with 50 years ago. And 50 years in the future, unimaginable. It's all about speed. We can do our job better every day. It's really exciting. So I wake up every morning, and at 8 o'clock, I get a report. Just like Steve gets weather from Mars, I get a report of what happened in the last 24 hours on our 4 search programs.
Does knowing where there's exoplanets, I mean, as we've heard from Dave, does that change how you might look, where you might look, for example? Or?
That's a question, and it really is a question. So as Dave has already said, the planets that we found first were big gas giants. And goodness, they were in short period orbits close to their star, not way out in the edge of the solar system the way it is in our case. And we think that they got close to their star by migrating in during the formation process of the planetary system. Well, if you've got a big, wonking, giant planet migrating in, might not be so nice for the terrestrials, right? It might take everything into the sun with it. And so for a while, it was a real question. Do the exoplanet systems, are they the best place to look or the worst place? Now, well, theorists are very, very fleet of foot, and there are some theoretical explanations that could tell us that even if you have a giant planet migrating in, terrestrials could still be there. They could reform after the giant went by, or they could actually survive the migration if it were slow enough. So exoplanets are now back on our list. The little planets, the M dwarfs that Dave is looking for a long time we said, no. This whole Goldilocks story, if you have a small planet, a small star, the planet has to be so close to the star that, like the moon is with the Earth, it will be tidally locked. Keep the same face to the M dwarf all the time. And that'll mean that you'll boil off any atmosphere on the front side and freeze it out on the back side. So that's not going to be a great place to live, even though they are the most plentiful stars. Well, again, that's...
I have to interject here. The reason we started looking at those low-mass stars is because of a paper you wrote.
I know.
And it was entitled something like, A Reexamination of the habitability of planets orbiting low-mass stars.
We do. We always reserve the right to get smarter. Right? And so we thought about it. A number of scientists thought about this. And gee, if you seed that atmosphere with a bunch of greenhouse gases, and you can get winds circulating, then you don't have such a dire situation. And you also may not have a one-to-one rotation and revolution lock. It might be some sort of a 2-to-3 ratio or something like that. So there are ways out of it. Again, though, you know, there are people who say, well, M dwarfs, they're nice when they get older, but the first billion years, they're pretty violent. And that radiation coming off of the star may, in fact, take off the atmosphere from the nearby planet. So there are questions, but nevertheless, we're looking. We're looking at stars like the sun. We're looking at systems that we know to have planets. And we're looking at the M dwarfs because those are our closest neighbors. But should we do something like transmit in reply? Okay. The folks that I work with, the scientists that generally work on SETI projects, have said, no, if we detect a signal, we're going to tell the world, but we're not ourselves going to transmit a response until there's some sort of global consensus about whether we should, because some people are in agreement with Steven and think they're going to come and trash the place. And then, you know, who should speak for Earth? What should we say? Those are very nice words, global consensus. You realize, of course, we got no way in heck that we know how to get that. But we try. And now maybe the great thing about the social networking technologies is it may be exactly what we need to hold a global conversation on this question. You know, we don't have to put people's butts on airplanes and trying to bring them to a conference center. And most of the world's traditions and cultures don't have the wherewithal and the finances to send people anyway. So maybe we can, in fact, have a global conversation about this question. And I think we should. As to whether or not their intentions towards us will be malevolent, I'm inclined to think if they've got the technology to get here, they're a lot older than we are, and they can't have gotten old without getting over the aggressions and being able to control their population and their behavior, something that we can't yet do.
Good, thank you, Jill. Thank you. So, we've now should move to our second part, a more general discussion about is there life out there. So, I mentioned in my introduction my colleague Christian de Duve. He said life is a cosmic imperative. Is that the case, or is it unlikely? Which side do you fall on?
We don't know yet. We just don't know.
You're on both sides. Yes.
We don't have, I can't put myself on a side. We have one example of life, us. Here we are. We know that life can arise. But does it happen all the time when you have watery conditions? Does it happen some of the time? What do you really need? We simply don't know. This is the reason that I'm pushing so hard to try to understand whether or not there was ever life on Mars, whether or not there's life in a place like Europa. Because if you can show that life arose independently is key, on two different worlds in this solar system, then when you consider the multitudes of other solar systems that are out there, it takes no great leap of imagination or faith or anything else to believe that it could be very commonplace.
When you say independently...
That's key.
Yes, because...
Well,
what about colonization from one to the other?
Well, not just colonization. You can simply... It's called panspermia, the idea that life can be transported from one world to another. We have lots of rocks from Mars on Earth. Okay? Those were ejected from Mars by impacts that threw rocks into space and they land on Earth. Same thing has happened, impacts on Earth, rocks go to Mars. Mars and Earth have been swapping rocks for billions of years. And those rocks go back and forth with typical transit times of tens or hundreds of millions of years, but some of them take 7 months. That's how long our spacecraft took to get to Mars. And life can survive in the vacuum of space that long. So life from Earth could have been transported to Mars. Or life from Mars could have been transported to Earth. We could all be Martians.
So in making, I'm going to come back to the others, but in making the decision whether the life is related, you would say if it was DNA-based, blah, blah, that would be evidence of that it is?
I don't know. I mean, let's say that life managed to get transported from Earth to Mars or Mars to Earth, I'll make up a number, 3.5 billion years ago. Divergent evolution, they could have gotten quite different from one another in that period of time if they're separated that much. So, I don't know.
You know,
Cosmic
Paul,
imperative?
I think anybody that would tell you an answer to that question would be over on that belief side. And that's the wrong verb for science.
I disagree with that.
Ah,
Very
all
good.
right.
Very good.
I mean, I'm not into belief. I think that the more we know, the less we have to believe. But the fact is, one can look at life as an entropy generator. There's an equation called the Rayleigh-Bénard equation, and you don't have to go to another planet to know that there'll be convection on a particular planet if you know some of the conditions. And like the same way, if you know that there's going to be a wet, rocky planet with a carbon dioxide atmosphere, then you have the Nernst equation to tell you that life will automatically onset, and it'll be pretty deterministic. It'll always do roughly the same kind of thing. It might not go as far as this, but I would say the only real major difference would be chirality. Otherwise, it's going to be very similar because
Can you
it's doing the
explain
same
what chirality
job. Chirality is whether
chirality is.
you have a left-handed amino acid and right-handed, well, left-handed amino acids and right-handed DNA.
And that's the shape of the
and that's
molecule.
the handedness of the molecules, and you've got to have that on this planet. But I think that it's conceivable that you would have an alternative chirality. And I absolutely disagree with the idea of panspermia, because we know in the lab how difficult it is to culture organic molecules. And if you come to that wet, rocky planet that was our planet 4.4 billion years ago, it was a desert, a water desert. It's very hard to think of something getting cultured there. It's the incumbents. We know this from all kinds of reasons. Incumbents always win. They hold the fort. So I think that it's a deterministic aspect of the universe. I mean, I wouldn't quite use Dedue's word, but I'm sure he's right. Go to a planet like this, when they're much rarer than we thought, but you'll certainly have life. And after all, you were getting excited about Europa.
Here's what I worry about, and I worry about this in my business where we look for life on Mars, and I'm sure Jill worries about it too. The phrase that I've heard to describe this problem is, I wouldn't have seen it if I hadn't believed it. You don't want to fall into that trap. You don't want to believe it to be true and therefore see it in your data.
It's just a projection of the Nernst equation. I mean, what's the problem? We're taking life too seriously. Life is an entropy generator. We know what it wants to do. It reduces carbon dioxide with hydrogen. And that's what you think about it. Everything you eat, everything you see has all had that effect. It's a quickened chemical reaction.
I want to believe it, but you're a lot more sure than I am.
I think it is a very modern point of view. When I lecture a big astronomy course, I always ask my students, how many of you think there's life elsewhere in the universe? And the overwhelming opinion now is that there is, in part because there's so many stars out there. And I just want to pause to say, and I understand what you're saying, but I want to pause to note that basically that's a very contemporary view. That's a very modern view. It wasn't 60, if you go back 40, 50 years ago, everybody knew that there were good reasons to think there was life on Mars, certainly 100 years ago. That wasn't better informed necessarily. If we go back 100 or 200 years, there were reasons to think the Earth was really special and alone, and there were very deep-seated beliefs. And so I very much side with Jill that we have to measure. And so what astronomers can do is we can go and find 10 or 20 planets like the Earth that are indistinguishable in terms of their distance from their stars, their masses, their bulk compositions. And if we interrogate each one in turn, and as far as we can tell, they're the same age as the Earth, they're made of the same stuff, and yet there was no genesis. It's a barren rock and a barren rock and a barren rock. I'm truly open to that possibility. And I think that would have very deep implications well beyond just science for how most of us view ourselves in this universe. Or we could find that every time the right chemistry sort of comes together, you have life burgeoning on the surface. But the excitement is that we can go and measure that. But I think that right now in the scientific community, both options are firmly on the table.
How would you stop it? How would you stop life emerging? How could you possibly stop it in this kind of condition? How could you stop convection if you can't?
I hate to bring it up in this audience, but it's the unknown unknowns.
Okay, but
it's the things I don't know about that worry me.
Okay, but we need to have a model to know what to look for. So what to look for, I mean, the old idea is somehow or other, life is a reorganization of organic molecules that rain in from space. Now, that is must be nonsense. So it's much more likely that, as I say, if you have a CO2 atmosphere and a rocky planet, then that's the likelihood of getting life, because then it has a job to do, an energetic job to do. So to me, and then you can say, right, that's a promising planet because it's got a CO2 atmosphere. I mean, one of the things about Europa is how much CO2 is in the ocean of Europa. Now, if there's plenty, that's fine. But if there isn't, to me, that would be very significant to know how much CO2 is in the ocean. Because if you don't have the CO2, where's the carbon coming from?
Well, I'm willing to buy the argument that habitable environments are commonplace throughout the universe. I'm willing to buy the argument that conditions suitable for the origin of life are commonplace throughout the universe. Fine. Emergence of life. But because I don't understand the process of the emergence of life, I am unwilling to just take it on faith, that life is going to emerge if the conditions are right. It's possibly true. I'd love it to be true. I want to do an experiment.
One last thing, if I may say, on that, and that is that all of life sciences, environmental science, and so forth, it's all missing chapter 1, because nobody's got whole. So let's try and work out chapter 1. So this is the point. And I mean, I think that perhaps maybe it's done.
Should we be...
Well, actually, I'd like to say that it seems to me we've got 3 astronomers here and someone who deals with a much more deterministic system than we tend to.
You can call me a geologist today.
All right. But I actually think what I'm seeing, and I thought this would be an oxymoron, that the astronomers are actually being a bit humble here. We've actually, we've actually had the experience of building new tools to look for something that we want to find out there. And we make the argument in our presentations and our solicitations that if we build something that can do this better than we've done before and do that better than then we're going to find this. And as astronomers, we've had this fantastic history of building a new tool and finding something that nobody in the world had any idea was out there. And of course, then we call it dark energy and dark matter and all that stuff because we don't know. But we find new things. We get surprised. And maybe that's why we're not quite so willing to say, oh, sure, yeah, given these conditions, same thing's going to happen all the time. It's deterministic. It's inevitable. You can't stop it.
What about the numbers argument? The fact that there's, billions possibly out there and there's so much time. Should we be impressed by that?
I think that, there's a fairly classic way to pick apart that problem, which is called the Drake equation. And basically what you do is you say, something along the lines of what's the number of the stars in the galaxy, what's the fraction that form planets, what's the fraction that form planets like the Earth, what's the fraction of those that go on to make life. And then, because you've parceled it up like that, then you can say, okay, well, we now have answers. We know the number of stars in the galaxy. And I would, to get to your point about, you believe that there are going to be habitable environments out there, I think that will be an answered question, largely because of the Kepler mission and the hard work of astronomers in basically 2 or 3 years. Okay? And that's very exciting, and that's a big factor. But there's that one factor at the end, which is what fraction of planets make life, let alone intelligent life. Okay? And you don't know. Maybe it's 1 in a universe, or maybe it's 50%. Okay, and that's chapter 1. And that's chapter 1. And they're just I have no idea which order of magnitude it is.
That's really the question.
Life makes waste, and you can always predict what the waste products are going to be.
So we know what to look for.
Surely you should be into that.
We know what to look for. Yeah, let's go look.
Right. But you need to know the waste products.
Right?
You can't just say, well, there's glycine out there in the interstellar space, and maybe life is being generated out there. You need to know that you're looking for waste products. So that is one advance from this kind of point of view.
Well, we were talking about global consensus a little while ago. I don't think we're going to get consensus over this particular issue with our 4 panelists. But just a brief diversion about history of ideas, because things have changed. I think I remember this correctly, but 300 or 400 years ago, when telescopes were first turned to celestial objects, often it was suggested there was life elsewhere.
Sure. Oh, yeah.
I mean, that was initially. Then it went down to there's no life anywhere, and then we had canals on Mars, I guess 100 years ago, then down again, and then up again. Is there any sense, I mean, why is this happening like this, up and down? Any thoughts on that?
Well, it's something that we all want to believe, right? I mean, the canals on Mars were evidence of intelligent life. The problem was just that the life was at the wrong end of the telescope, okay? So we want to believe it. We want to believe it, and it's very important as scientists to not let your interpretation of the data be too colored by your desire to find an attractive answer.
Okay, another question. Are we being blinded by our knowledge of what life is like on this planet? I mean, in other words, are there other types of life we could imagine that perhaps haven't thought enough about how we might detect them? And this, of course, begs the question of what life is, which I know we rather glossed over.
Oh, yes. Yeah. When I'm talking as an astronomer about finding life, I think that the argument essentially boils down to that the chemical signatures that we see in the atmosphere and the bulk properties of the planet are so like the Earth, and that the origin of those molecules on the Earth is life, that we just argue that the simplest explanation is life. But we would have no ability to look at a planet that had substantially different life and infer that it was alive. So the only kind of life that I think in the foreseeable future that we are going to be sensitive to in any meaningful way, I mean, you can make more general arguments about chemical disequilibrium and all that, and those we can debate, but I would say the only kind of life that we could truly point to and make a good case for that maybe, someone who actually gets to dig in the dirt might believe, and maybe not even then, would be only life as we know it on the Earth. So it's a very limited view.
There's a simple, practical element to this as well, and that is the things that we do. The telescopes like Kepler, the rovers like Spirit and Opportunity, the arrays that look for SETI signals, these things cost a lot of money. Our rovers cost $800 million, and that's a cheap mission, okay? And so if you're going to try to design a mission, get a government agency to trust you with hundreds of millions of taxpayers' dollars to build something and put it on top of a rocket and send it into space, you better have a pretty good explanation for what you're looking for. And I can't imagine trying to get funding to do a multi-hundred million or multi-billion-dollar space mission to look for some kind of life different from the life we know. I wouldn't know what to look for. I wouldn't know how to sell that mission. I probably wouldn't get it sold, and I wouldn't get it launched. It might be the right one to fly, but I don't know what it is.
But if you're going to try that experiment, you should at least first try it on Earth.
Yeah.
Because there are environments where life as we know it apparently is not existing.
Well, such as?
Well, it's not clear whether the Atacama Desert is a place which is so dry that really is no life, or that we...
No, it's detectable, honestly. Take my word for it. It's detectable. One of the paradoxes
I have a colleague who would argue with you, but that's okay.
Bring him on.
You're here. We'll take your word.
So the point, I mean, you're quite right about what you're saying about the priciness of all this, but if I were to say from an origin of life perspective, the ratio of the money that's spent on astronomy and cosmology and so forth, and the amount of money that's allowed through funding of origin of life, I mean, it's extraordinarily low. People just don't want to fund origin of life, and yet you need to understand that for what you want to look for. So I would say perhaps you could speak up for this kind of research.
I agree with you 100%. Some years back, when I was just working on the Cassini mission to Saturn, I went on a cruise on the Atlantis II, which is the vessel that supports, of course, the Alvin deep submersible. Magnificent vessel has done marvelous work at those deep sea vents that you mentioned. And one night, late on ship, some of my shipmates, who were people who studied these deep sea hydrothermal vents, asked me, so how much does that Saturn ring mission thing you're working on cost? And I told them, and I thought I was going to get thrown overboard right out there in the Pacific. $3 billion.
So Michael, what what about this idea of a shadow biosphere? What's your take on this?
It's hard enough to try and work out what's going on with, I mean, if you're talking about a shadow, are you talking about you're talking about Paul Davies's idea that maybe
it's not just Paul's, but yeah, different metabolisms, different
it's
biosolvents.
It's hard enough to work on this one. But it looks as though that all the metabolisms you look, I mean, there was 2 beautiful papers in Nature this last 2 months by the Fuchs group showing that if you go back right down the bottom of the evolution tree as far as they can go, they couldn't find any enzymes that broke down molecules. They were all anabolic. They all made it from the bottom up. And if they look at the pathways, they're all the simplest. The simplest pathway is the one that makes acetate. It costs only 1 ATP. It's extremely simple. How could, if you were going to design it from scratch, that's what you'd do. And in fact, you can do most of that in the laboratory anyway. So I would say that it's actually looking at us in the face, a lot of this. And because of a peculiar history of the Oparin, the idea of a kind of, I'm not talking politics, I'm merely pointing out about philosophy and ideology and method and how they seem to come together in the 20s, 30s, 40s, and eventually in 50s to suggest that life somehow or other came down, organized itself, coagulates on the surface of an ocean. And that ruled for about 80 years. I mean, I think that you won't find one of those papers quoted in the biological literature because they said proudly there is no evolutionary relationship between prebiotic chemistry, whatever that is, and life. Whereas these kind of systems that deal with inorganic origins of life do have, you can segue one from the other. I'm not saying it's seamless, but you can definitely see the directions. I mean, you can see that the minerals that are precipitated these vents have exactly the same structures as some of the metal enzymes like ferredoxins and acetyl-coenzyme A synthase. They're extraordinarily similar. Everything was on a plate at a hydrothermal vent, and it's doing, and I just keep saying it, it's doing a job. So it makes sense, just like convection makes sense. Conduction only can do it so much, and if you put a bigger thermal gradient, you automatically get the onset of convection, and you can predict when it onsets. And I would say the same would be for metabolism. And we don't need to worry about more peculiar metabolisms because people haven't studied hard enough this one.
Do you think it's worth exploring tens or even hundreds of kilometers under the surface of the Earth for non-DNA based life?
If you're talking about Tom Gall's idea,
yeah,
which he did change to quite a bit. No, I'd say life probably goes down to 15 kilometers. It goes down to where, that would be an absolute maximum. 4 or 5 kilometers is more likely. But when life first started, it probably, if you would appreciate the hydrothermal vent idea, it probably then went into the deep biosphere. The ocean was a desert. Actually, even now, there's not that much, not much going on in the wide ocean. It's only at the downdraws and the updrafts, convection cells that really, and that's what the fishermen go for, of course. So, no, that's the case.
I mean, if you go to other planets too, places like Mars, the best place to look for life today may well be fractures deep down below the surface. If that methane in the atmosphere is indicative of biological processes, it's probably biological processes at some depth.
So there's an interesting thing about your discoveries. These are extraordinary discoveries of carbonates. So you've got magnesium carbonate and iron carbonate. It's fantastic. And then, I haven't seen this paper yet. Just came out.
Just came out today.
Okay, right. So I'm behind the times. But could you think that you were suggesting that you probably had an acidic, any kind of water on the surface was probably acidic? Isn't it likely that you've got an alkaline solution interacting with the mafic rocks, the basaltic rocks? And in fact, what you're bringing together is you're neutralizing 2 solutions and therefore precipitating a carbonate right there.
Yeah, it's going to buffer the acidity. The other thing is that there are indications that the acidity on Mars changed with time, that very early on, the waters were more neutral, and then as time progressed, some of the younger rocks is where you see the sulfates, the clear evidence of more acidic conditions, probably associated with extensive volcanic activity that was going on at that point.
So my final question to the 4 of you, the more philosophical one. So let's say we get a signature of life out there. Would that change how you would view yourself, how we should view humanity?
Are we talking technology or pond scum?
I think we're talking, how would you view yourself if there was another life form out there?
Well, no, but I'm asking how complex is this other life form? Can it talk to us, or is it just...
Well, you can answer both.
Okay.
If it can talk to us, yes. If it can't talk to us, what would you answer?
Well, I'll give you an answer from a Martian perspective, because that's going to be at best in the pond scum variety.
Yep.
You know, I think what it comes down to is, could we find compelling evidence that life on Mars arose independently on Mars, that it wasn't somehow transported from Earth? And I know you're skeptical about the panspermia thing, but I think you have to treat that hypothesis seriously, because the implications of life arising twice on two separate worlds just in those one solar system, that's so profound.
So how is that question I'm asking?
Yeah, because if it arose twice or maybe multiple times in just the solar system, then this gentleman is right.
So
then he's right.
So the great test of that, but one would be very lucky, and that is if it had the opposite chirality. Then
sure, and that'd be a great way to do it, because that would show that they were really two different independent origins. But if you can show that it happened twice just in the solar system, then given the number of planets that are being found out there, then it's almost inconceivable to me that the universe isn't just teeming with life. So to me, just one viable microbe from Mars that didn't somehow originate on Earth has just profound implications.
Yeah, I do think that, you know, why do we have astronomy, right? Well, I think what astronomers have done, what we can contribute, is to put the human, you know, experience in perspective. And, you know, one thing astronomers have told us is that the length of the human experience, the length of an individual human lifetime or all of humanity, is a tiny, tiny fraction of the lifetime of the universe. That's something we didn't know, you know, and really makes us feel quite small. I think the other thing astronomers have contributed is putting in perspective our physical size, that we are on a nothing planet orbiting a totally unremarkable star, and that we, our physical beings, are just negligible in terms of the matter content of the universe. I think the question of life would actually be more important than either of those. If we found out that life was an inevitable natural consequence, and that we were but one of many islands out there in the galaxy, that we were living in a biological universe that had no trouble delivering life, and that we could someday, even if not in our lifetimes, imagine coming into contact with that not having a conversation, but actually reading it and studying it. That would lead us to view ourselves very, very differently than if we found out that, to the best of our ability to build telescopes and go out and measure, we were truly alone and that the Earth was it.
So are you suggesting it's a kind of consolation that there'll be more life out there, or more worrying, or make us, or our vanity would be displayed, or what? Sorry, I didn't quite get your point.
I think my point is that we would view ourselves very differently if we knew that our planet was the only... Oh, because you would, well, because you would truly think that, you know, biology on the Earth was, that there was something we didn't understand that wasn't just chemistry.
Would it make us feel, you know, astronomy is gradually moving us from the center of the universe, you know, and we're gradually getting more and more insignificant. Would it just make us even less significant, or how would you feel?
I mean, you know, be more wonderful. I mean, things will get more wonderful. As we lose the mystery, things become more wonderful. That's what science does. So I would think, yes, it'd be more wonderful, and I fully expect the second point you made.
But you think it'll be more wonderful whichever outcome is true, or you can't even conceive of
I can't even conceive there isn't life. I think we're taking life much too seriously to think that we're the ones. You know, of course, to me,
so it's inconceivable to you. But to me, they're both on the table, and I'm torn apart. I'm up at night worrying about this.
I'm with Steve in awe of that pond scum on Mars. If that should turn out to be a second Genesis, it's phenomenal. But I think that SETI, this question of are we alone, being asked in terms of sentient beings somewhere else who can create technology, or at least those are the ones we might have a hope of discovering. I think the search for them, even if we don't find an answer, is incredibly important, because I see it as holding up a mirror to the entire planet. And when we talk to people and we get them thinking about the potential for intelligent life elsewhere. What we see in that mirror is us, and we see that we are all the same when compared to something that has an independent evolution somewhere else. And so I think it's really important. That's why I love to tell this story, because I hope that it helps to trivialize the differences among humans that we find so difficult to deal with today. So seeing ourselves as all the same, seeing ourselves as earthlings first, I think is an important message.
I think this is the right place to finish. I want to thank you, the audience, for coming. I want to thank our great panelists. I think we've had a really good discussion. So thank you, Jill. Thank you, Michael. Thank you, Dave. Thank you, Steve. Great evening. Thank you.